Hi there, my name is Ravela, and together with Kshitij, I'm going to talk to you about the Sloop system with some deep learning experiments that we've done in its context. The Sloop system is a very classical system by this point. It's been around for several years, and it's been functioning excellently, and we thought that if we could advance the technology by applying deep learning directly to it. And so this talk is a result of some initial experiments in that direction for this workshop. Our group is the Earth Signals and Systems group at MIT, which I direct, and we are focused on autonomy, learning, information, vision methods for application to Earth, planets, climate, and life. We are vision scientists, we are control theorists, we are roboticists, we are earth scientists. It's an interdisciplinary group. And some of the projects we do involve autonomy with respect to mapping the environment, using machine learning and physics to quantify risk from extreme events such as cyclones, and most recently looking at learning from a dynamical systems perspective. This is just by way of overview, but the project that I really want to talk to you about is with respect to animal biometrics and the Sloop system. Sloop's pioneering vision was to use generic visual features for recognizing individual animals and to adapt them into customized high recall strategies. And without such adaptation, the high recall was simply not there. And prior to this idea, there were customized ad hoc methods in play. The idea priority that we claim is that high recall recognition requires a coupled human-machine retrieval strategy. And there have been several other researchers who pointed to fully automated solutions. We just don't buy it. And that even dealing with non-stationary populations, perhaps especially dealing with non-stationary populations, requires, again, a coupled human retrieval strategy. The distinguishing aspect of our approach, therefore, is to incorporate relevance feedback to improve performance and deliver high recall, which many conservation applications demand, and to use crowdsourcing as a way to scale relevance feedback, and that this crowdsourcing is self-selecting. Another aspect of this distinguishing approach of our work is that we want to target questions for maximizing information gain with respect to the system. And thus we want to ask sparse questions. And we've gained rich operational experience in this application of the Sloop system. And in the rest of the talk, I'm going to take you under the hood and describe a little bit about the system. Sloop's history, in fact, began in 1996 in image retrieval. Back then, it was just a starting field, and we did a lot of work in multi-scale differential features. And that work then led to a first paper on recognizing individual salamanders, which was pioneering at the time. And after that, it was led to immediately to biological application. By 2007, we had finished a survey and a study in field application of the method. By 2008, we reincorporated earlier ideas in relevance feedback, and we saw dramatic performance gains. And by 2009, number of techniques from local features to diffeomorphic alignment in conjunction with these ideas started making it into our system. By the time 2012 rolled around, we were operational, and this is published news. And by the time we reached 2013, we provided scalable crowdsourcing. From that point in time, we've been scaling to multiple species and multiple applications, and our focus mostly has been on small species where the recognition problems are particularly challenging, both due to the fact that they tend to be non-stationary distributions and they tend to be of the kind where recall is really important. Sloop has an enormous set of features. Largely, it's an application. It is a tool for biologists to produce a capture history that can then be connected up with more statistical analysis. It can reach, order 10,000 sized identities, and is focused on small and endangered species. The processing is organized in terms of workflows, and the system provides a number of benefits and features in terms of how these workflows could be organized, starting all the way from uploading with text metadata and categorizing views and performing customization with respect to processing in asynchronous versus batch and so on. There's a number of pre-processing tools, including, for example, the specularity removal tool that you see here, and these are noted on the slide. Multiple representations have made it over time, and we were one of the first people to say that, there's not a single solution that would fit all. There were competing responses at the time that just said, well, we have one method that could just spot for all animals, but that doesn't really work, we felt. And so we started incorporating customized strategies. And we focus heavily on the use of relevance feedback and to optimize that process. Sloop is organized around two servers called the DEI and IPE. The DEI stands for the Data Exchange and Interaction Server, and IPE stands for the Interactive Processing Engine. IPE really ingests all vision code, and DEI really organizes all the biologist work. And the architecture diagram that you see has been published, and you can read the paper to read more about it. But it's a good coupling between citizen science, the biologists, and by citizen science we also mean crowds. But crowds mostly are focusing on the upside, whereas citizen science mostly focus on the day side. And we have a mechanism by which this system can run in the cloud as a distributed server with shared computation, as an embedded system in the aircraft, and a number of other possibilities, or as a light on a desktop, number of other possibilities are feasible. If you are interested, please let us know, and we'd love to work with you. A key part of Sloop is that the biologist owns their data and they manage and the privacy is managed for them, but our system offers a service wherein it goes, figures out what execution needs to be done, does the execution, and then moves the image in its path, in a finite state diagram. You can think about it as an image being advanced to eventual recognition. The key aspect of Sloop was, as I keep mentioning, is relevance feedback, and you can see that in these graphs, and these are published accounts, and you see the uniform lifting of performance as a result of a relevance feedback, and these gains are uniform. So the question we start with is, what are the clear roles or potential for learning, and what role does it have in recognition? We can first of all say that, well, we want automation for high recall. Clearly, that's a goal. We want scaling of processing. We want to learn from feedback online, and we want to handle non-stationarity. When we think about deep learning, these are the questions that come to our mind. Can we handle high recall? Can we process the scale? Can the scaling be, processing be scaled? Can we learn from the feedback the user will inevitably and must provide in many cases? And can we handle non-stationarity? I just do not belabor the point. These are the places where we think of the role that deep learning can really be useful, if it is to be useful. So we tried a few experiments. The first one was we constructed a Siamese network, and we applied this, and you're familiar with what a Siamese network is, and the architecture shown here. And we had two ways of applying it. One is at the end, after stripping the last layer on AlexNet in the Siamese network organization, we would either use an SVM and apply that to stinks, or use a triplet loss function and apply that to geckos. So this was our nominal network that we call let's see what happens. The second network that we tried was based on this technique of diffeomorphic alignment. And you see here how the diffeomorphic alignment is being applied to morph one image to the other. And in the picture, you see that image 1 and image 2 initially are quite different, but after the morphing, we get the same image. And so this transport distance that is estimated by diffeomorphic alignment really is useful because it's much better than actually solving transport, because these things are not conserved. And at the same time, that transport provides a useful feature for discussing, for determining how similar two patches are. And this is well known. You can see our ICCV09 paper on it. Okay, so that's the second technique. We use that as a control. And the third technique we had to think about was to take two images and calculate the transport and the divergence of the vector field, and then the absolute amplitude difference between the two. So one is really about brightness differences, or it doesn't have to be brightness, it could be any feature, and the other is about transport. And we take this one and we apply it to a shallow CNN with ReLU activation, followed by fully connected layer, softmax, and classification. So the three ideas are, one is to use a standard run-of-the-mill network and the Siamese twin configuration. The second one was to use a new feature, and the third one was to pre-process the network with these customized features. Our hypothesis was that the first one should really work well because we really just used a standard configuration. We took AlexNet, we applied transfer learning, we stripped off the last layer, we made it into a Siamese twin, and we expected to get reasonably good results on a reasonably small data set, which is our Gecko data set. And you can read the paper for more details. Here's what happened. The Siamese twin version completely bombed with triplet loss or SVM. The performance was not much better with SVM, and with the triplet loss version on geckos, it was 58%. And we're not yet trying to explain this result, but let's compare it with the control run, which was just to use deformation features. You take image A and B, you deform them, you calculate some norm on the deformation vectors, and you use that to rank images. Okay, so this is a simple idea. It's often used in conjunction with other algorithms, as we've done in ICCV09, but even just applying it by itself gave us almost 69%, which suggests that the Siamese version really had some trouble. But consistent with this idea that deformation features are applied with other algorithms, we describe field errors as errors in amplitude and errors in deformation, and we prime a very shallow CNN, a 3-layer network with these features, and immediately, lo and behold, the results bump up to 90%. So what does this mean? I think the jury is very much out. On the one hand, how are we supposed to optimize our networks if priming with reasonable features, these are not crazy features, they're just brightness errors and deformations, could produce such a result with really shallow networks, then what is to be said about very deep networks that have been pre-trained, involves all sorts of steps, whose optimization, whose construction, whose structure is non-trivial by most accounts, and to us seems a bit of alchemy. So if this is true, then what can we say about using deep learning for individual identification? Is there a systematized process for this? It's not clear. And end-to-end learning with deep networks, we feel, is quite brittle. The performance has been quite brittle. And it can be frustrating, in fact. Now, the more important point I want to point out is that, it's unclear how to incorporate relevance feedback as, any system is applied. Whether it's mostly in our case with respect to non-stationary population distributions, as new members keep coming in every season. But even if in the case of the stationary population distribution, also known as re-identification, you might wonder what happens when there's a mistake and how relevance feedback is incorporated online into the learning system. Well, this doesn't seem to have an easy answer with respect to deep learning. In fact, the deeper the network, the harder this problem might be. Although we can't say that for sure, it seems like it would be harder. And so we feel that the jury is very much out. I've perhaps presented a contrary perspective to the other papers or presentations in this workshop, which is that, insofar as identification, individual identification is concerned, for high recall and with respect to incorporating relevance feedback, it seems like Sloop's classical approaches are still very much in the game. Thank you so much.